interest. You can't be working at the BBC and also selling products to the BBC. By having wide even dispersion, so the frequency response does stay the same off axis, helps the speaker sort of disappear into the room. In these, we're using a 19mm dome, so it's much narrower dome, which means we get much wider dispersion at very high frequencies. At its core, a transmission line is a long pipe that is open at one end, and you place the bass driver at some point along this pipe. Okay. If you just design a straight pipe and stick a drive unit in it, it sounds really horrible. So I think something that people forget about transmission lines, a massive benefit, is actually the mid-range clarity is incredibly good, because you don't have this mid-range distortion of sound coming off the cone, bouncing around the cabinet, coming back through it. It goes into the cabinet, gets absorbed, and it disappears, and it's incredibly clean mid-range that you get from the cabinets because of that. Okay. So there's a parameter in fluid dynamics called the Reynolds number of the system. What causes turbulence is a difference between the friction at the boundary and the lack of friction in the centre. So the wider the gap between these two, the more of a gradient you get, and that's where you start getting slow air and fast air, which then starts rotating on itself and causing turbulence.
Hi there, it's Allan here from Glasgow, and I'm delighted to be with Toby, who's one of the head R&D engineers at PMC Loudspeakers. We're here to chat about a little bit of background to PMC, and Toby's going to be kind enough to talk us through some of his fabulous product. So without any further ado, Toby, can you give us a little bit of background to PMC and kind of where the company came from?
Yeah, sure. So PMC as a company was founded by Peter Thomas and Adrian Loader. Now, Peter Thomas at the time was working at the BBC. I think he was studio manager at one of the studios. It might have been Maida Vale, I can't remember exactly which one. But at the time they were going through a big process of refitting some of the studios, and we're trying to find a new set of main monitors that would not only meet the SPL requirements they had for these studios, but also not sound horrible, because a lot of the larger main monitors at the time were big horn-loaded things that sounded very brittle, not very hi-fi, not very nice, not very accurate. So they was just getting very frustrated by the fact they couldn't find a speaker that really fulfilled all of their requirements, and I think he had a very big passion for transmission line loudspeakers at the time, and him and his friend Adrian started in their back garden designing and building prototype speakers because for fun, and then they sort of ended up working towards this design that started sounding really good, and they brought it into Pete's work, trialed it in the studio, and realised, this actually could be exactly what we're looking for in the studios. Maybe we should form a business out of this. Now, conflict of interest, you can't be working at the BBC and also selling products to the BBC, so they had to make a big life decision, and chose to quit their job, sell the speaker to the BBC. That was the first product that PMC ever made, the BB5 active main monitor loudspeaker, and that's the birth of PMC. So it very much was starting with the studio business, and our heritage really is in the recording industry. So
and that's still quite a big part of your business, isn't it?
I'd say it's probably 50-50 still. So we have a very much like a 50% split between studio monitors and that whole side of the business, and then the domestic products, which came I think it was after sort of 4 or 5 years of producing just studio monitors, we started breaking into the hi-fi market. Now at PMC we've always had a really strong ethos of making sure that you can, if you buy one of our domestic products, you are really getting the same sound quality, the same voicing and the same tonality that you would get from our studio products. One of our big taglines is we are the music makers, and we want that customers who are having our products in their homes to really know that they are getting the exact same sound that their music was mixed on and mastered on with PMC monitors.
I mean, kind of rightly or wrongly, there's a kind of conception that studio monitors can be a bit clinical, they can be a little bit hard. They're more tools rather than something to give you pleasure. Where do you guys sit between kind of voicing for a studio monitor and voicing for a more domestic product?
Totally. I mean, there's always going to be a slight change of priorities when you're designing for a studio or designing for a domestic product, but we're very strongly of the belief that any good loudspeaker should be usable, should be accurate, right? Any loudspeaker should be accurate and should be pleasant to listen to. So even if it is for a studio monitor, we don't want our products to sound clinical and hard. Even if they are revealing and accurate, they still have to be enjoyable, spacious, engaging to listen to. And yeah, we just really have a very strong idea that all speakers that we design should sound similar, even if there are slight.
I mean, are those voicing changes as much to do with the immediate environment in which you're listening to? Typically, a studio will be a heavily treated room.
Absolutely,
to stop
yeah.
reverberation and stop decay and.
Absolutely, we know for a fact that. The acoustic environment you're going to be listening to a studio monitor in is likely to be, as you say, a lot better damped than average listening room. So you'll pay attention a bit to that in the voicing. So maybe you'll allow a little bit more upper mid-range, say, into a studio monitor because you know that it's going to be well damped. It's not going to make the speaker sound too hard in that environment. Whereas in a domestic environment, maybe that might be a bit too much. But again, we have a lot of our customers will take our studio monitors and bring them into their homes,
of course.
and they still sound excellent there because, as I say, we've made sure that it's still a spacious and engaging listening experience. I think a lot of it is to do with the dispersion characteristics we aim for in our speakers.
Okay.
So we're really focused on the fact that we want our products to have a very wide and very even dispersion from the lowest frequencies up to the highest frequencies as possible.
So what do you mean by that? So the signal, there's no peaks and troughs in terms of the frequency response?
No, so in terms of dispersion, so I mean, yes, we want a flat on-axis response as well, but in terms of dispersion, it's so that we want it to be so that as you walk around the speaker, so as you go off axis from the speaker, we don't want the frequency response to change too much. So we don't want it to suddenly have a dip in the response off axis or to suddenly start rolling off very heavily at high frequencies off axis. So we want as much as possible for the tonality to stay the same as you go off axis from the speaker. Now that's really important because when you're listening to a speaker in a room, particularly a less treated room, you're not just hearing the direct radiated sound from the speaker, you're hearing reflected sound off the walls, off the ceiling and the floor. And as much as possible, you want that reflected sound to have a similar tonality to the direct sound. I think it's one of the things that our brains pick up on quite easily is if the reflected sound from the walls somehow is wrong and not matching well with the on-axis sound, and that can really collapse a soundstage if that sound doesn't match well. So by having wide even dispersion, so the frequency response does stay the same off-axis, it really helps the speaker sort of disappear into the room and feel more spacious and more real.
Okay.
So that's something we're aiming for, again, on studio monitors and in the domestic products, which helps sort of keep that same sonic signature throughout.
Okay, so there's a bit of consistency, but that'll work as well in kind of the sort of primary listening space.
Totally.
But also means that off axis, if you're sitting to the side,
we really
you're still getting a really good
really want to avoid that situation where you have one hotspot listening position where you have to keep your head locked in a vice. Yeah. We don't want that. So by having this wide and even dispersion, it means you can sit sort of 3-4 seats across a sofa or something like that, and everyone gets the same tonal experience. Obviously, just through audio physics, you're going to be pulled more towards one speaker or the other if you're sat way off axis, but the tonal experience should still be the same. So you're not getting sort of weird peaks, troughs, or a soft sound or a hard sound and all that sort of thing.
Okay.
So, yeah.
And so what are the mechanics of the tweeter that kind of help you achieve that? How does a PMC tweeter differ from perhaps another manufacturer's or another approach?
Sure. So there's a few main parameters that would focus on to try and achieve wide dispersion, especially up to high frequencies. It gets quite difficult. So there is quite a simple bit of physics which determines how at what point any drive unit is going to start narrowing its dispersion. This is just related to the wavelength of the frequency you're playing and the diameter of the driver. So as the wavelength approaches the diameter of the drive unit, it naturally starts to beam because you get reflections off the sides of the driver that start cancelling the waves off to the sides, basically. So the way to get very wide dispersion up to very high frequencies is to use very narrow drive units. Obviously, it's why you have to have a tweeter one of the reasons you have to have a tweeter and a bass driver, or a tweeter and a mid-range and a bass driver, is because if you try to play all your frequencies off the bass driver, it'll become like a laser beam at very high frequencies, which is contrary to what we're trying to achieve. The other thing is baffle profile and baffle width. So the narrower your baffle, generally, the wider your high frequency dispersion will be. When your drive unit is producing sound, it's not, as I say, it's not just going straight forwards, it's also rolling off to the sides and spreading out, certainly at low frequencies, and almost a sphere of sound. That sound will roll across the baffle of your loudspeaker and re-radiate from the edges. So related to the baffle width, there's always going to be some sort of cancellation, some sort of notch. The narrower the baffle is, the higher frequency that gets pushed, and the less of a negative interaction you get between the tweeter and the
I mean, that is one of the kind of characters of the loudspeaker,
Yeah.
which is a very domestically friendly aspect.
Definitely,
that
yeah.
kind of small face.
Yeah, and especially as you
it
move
were.
to
But, yeah.
some of our higher end products like the Fact
Indeed.
range, we really were trying to focus on how narrow can you get a loudspeaker whilst maintaining bass performance. I mean, going to a very narrow baffle sort of requires that you go to quite small bass drivers, which could lead you to having very poor bass performance. But because of obviously our core technology being, as I'm sure we're going to get onto, the advanced transmission line, it allows us to get a very narrow baffle with smaller bass drivers, but then keep a very, very good extended bass response with low distortion and sort of high output, which is nice to have.
The other thing we were talking about earlier was kind of crossover points as well. So you guys cross over your...
Yeah, so I think typically it's fair to say on a two-way loudspeaker, I think most people might think of crossing at say 2.5 kilohertz to protect the tweeter from overexcursion and that sort of thing. The problem with crossing a two-way speaker at that high is that you're starting to run into the point where the bass driver is already starting to beam, so it's starting to narrow its dispersion. Now, if you cross over at that point where the bass driver is beaming, and then cross to a tweeter where it's suddenly got very wide dispersion, you get this really weird sudden shift in the dispersion of the loudspeaker. So as you move off axis from the speaker, instead of having the same tonality as what you had on axis, you'll suddenly find that your output starts dipping towards the top of the woofer's response, and then it'll jump back up as the tweeter comes in with its wide dispersion. So you get this really odd off-axis frequency response. So to counteract that in our two-way products, we end up crossing our speakers much lower than you might expect. So I think the 25 series we're crossing at about 1700 hertz, 1.7 kilohertz, which is very low for a two-way product. That could lead to power handling issues and tweeters blowing up, which we don't want. So we've got quite a special tweeter design in these, and split in the 25 series, where we've got a very narrow dome, again to try and help with the wide dispersion. So most dome tweeters that you'd see in most speakers would be around a 27 millimeter dome. It's kind of like a good balance between dispersion, power handling, all that sort of thing. In these, we're using a 19 millimeter dome, so it's much narrower dome, which means we get much wider dispersion at very high frequencies. And then we use a very wide roll surround on that tweeter, which gives it incredibly high linear excursion. So it's a very odd design. Normally a tweeter just doesn't move, or relatively speaking, it's still not moving compared to the bass drivers, but it has probably sort of double the X max of a normal tweeter. So you're compensating for the small dome and displacement with more excursion, to get the sensitivity back up. So actually it's got more sensitivity and more low frequency output capabilities than some of our older dome 27 millimeter domes, even though it's narrower. So that then lets us cross it lower without worrying about power handling issues.
Interesting. Okay, and obviously that takes us neatly onto bass driver and transmission line and so on. So can you give us a little bit of background? So what is transmission line?
I mean, it's no secret. Every speaker PMC has ever made and probably will ever make has featured a what we call an advanced transmission line. We call it advanced because of all the many years of development we've put into it, which we think now merits the use of advanced. At its core, a transmission line is a long pipe that is open at one end, and you place the bass driver at some point along this pipe. Now, at frequencies related to the length of this pipe, it will resonate and create a quarter wave resonance that will cause the air in the line to stiffen and couple to the back of the bass driver.
And what's the kind of benefit of that then?
So when around those frequencies where the air is coupling to the back of the bass driver, what happens is it stops the cone motion and all the acoustic energy starts coming out of the transmission line vent. Now, the really important thing about the fact that the driver motion is reduced around these frequencies is that most of the distortion in any loudspeaker comes from driver excursion. The more drive unit moves, the more distortion it's producing. The less linear it's going to move, it might start rocking, it might start flexing. So at the lowest frequencies, which is where we're tuning these transmission line cabinets to, instead of the distortion going up, now normally as you go down in frequency, your excursion of your bass driver gets exponentially larger, so your distortion products get exponentially higher. Instead of that happening, as you go down in frequency, the transmission line starts taking over the sound production from the bass driver, the driver excursion goes down and down and down because the transmission line is coupling more and more strongly to the driving unit. Instead of your distortion going up, your distortion actually goes down. So we have incredibly low distortion deep bass from our cabinets, from a surprisingly small bass driver. Now, the inside of the transmission line cabinet is heavily lined with very high specified acoustic foams. So these serve multiple purposes. The first is they damp the fundamental resonance of the line, so it's not very peaky. It ends up having a very broad resonance over usually an octave or more. So you get these.
Is that the kind of level that you can get? That's the kind of spread you can get?
It's surprising, yeah. So you might, as I say, we're talking about with ported speakers, it can be a very high Q filter resonance. Very narrow, so a very narrow band of frequencies. But this on the transmission line is a very broad, very low Q resonance, which means that the time domain performance is really good. So they start and stop incredibly well because the whole system is incredibly well damped by the foams. Now, a side effect of having all these foams inside the cabinet is that it's not just bass energy that's coming off the bass driver. So we've got mid-range frequencies coming off the back of the bass driver, which we don't want to go bouncing around the cabinet and coming back through the cone. So instead, in the transmission line cabinet, because we've got all of these acoustic foams to damp the main fundamental resonance, the mid-range energy coming off the back of the cone goes into the cabinet and gets absorbed by these foams. So I think something that people forget about transmission lines, a massive benefit, is actually the mid-range clarity is incredibly good, because you don't have this mid-range distortion of sound coming off the cone, bouncing around the cabinet and coming back through it. It goes into the cabinet, it gets absorbed and it disappears, and it's incredibly clean mid-range that you get from these cabinets because of that. So yeah, there's multiple benefits. I think I've really only touched the surface there. They are incredibly complex to design correctly. It sounds on the face of it really easy. It's a pipe that's open at one end. Sure, just make it a certain length that corresponds to a certain frequency. If you just design a straight pipe and stick a drive unit in it, it sounds really horrible. You get all sorts of peaks and dips in the response because the quarter wave resonance, it's more complex than a Helmholtz resonance. It doesn't just resonate at one frequency, it resonates at one frequency and then every odd multiple of that frequency as well. So you get lots of peaks in the response. So we have to do all sorts of quite complicated design processes to.
So how do you manufacture? So is that in the foam design? Is that in the design of the pipe?
So many different parameters. So the foam design is one. So we spent ages and ages placing different thickness pads in different parts of the line, and then going through. It's a hugely long iterative process to get the right design of that. Then it's the exact shape and cross-sectional area of the transmission line at every single point down the line. So it's not a straight pipe almost every time. It's going to taper from a certain length to a certain width to a certain width at the end. And there might be increases at certain points to have certain acoustic effects, and there might be decreases at certain points to have other acoustic effects. Other things you can do is introduce extra chambers inside the cabinet to absorb very specific frequencies. So we might have, certainly in the 25 series behind me, there's and a lot of these cabinets, there's extra chambers inside the cabinet which absorb certain frequencies that otherwise would come through as a problem. There's an awful lot of different things we can play with to get a linear response and low distortion. It makes them very difficult to design. We've been doing it for a long time, and we think we've nailed it.
Obviously, kind of one of the kind of characters is this very typical throat as well. So I think there's some interesting design in that as well.
Yeah, that's a development that we brought out initially on our QB1 main monitor. So
that's one of the studio monitor products.
Exactly, yeah. So this is a similar thing where we're talking about having the same ideals and sound and everything from our studio monitor to our home products. They share technologies as well. So around the tuning frequency of the transmission line, as I say, the drive unit's not really moving much, but all the acoustic energy is coming out of the transmission line vent. That naturally means that you end up with quite high acoustic velocity out the vent.
A lot of turbulence as well, I would imagine.
Absolutely, yeah. So the higher the velocity, the more turbulent the system becomes. And turbulence manifests as high frequency noise that you hear as chuffing. We don't want that. So what this part is in the exit of the vent, we call it a Laminair vent. It's a nice trademark name for it. You've got to have that. But basically what it does is it splits the vent opening into multiple smaller diameter channels. So you end up with a very high perimeter. So a very large perimeter for the compared to the area of the opening. So you're increasing the amount of surface area there. What that actually does is, so there's a parameter in fluid dynamics called the Reynolds number of a system, which is basically it's a unitless measure of how likely a fluid flow system is to have laminar or turbulent flow. The higher the number, the more likely it is to be turbulent flow. Now, one way of reducing the Reynolds number of a system is to increase the ratio of the perimeter to the surface area.
Which is kind of counterintuitive, because you would
Sounds
imagine
weird.
you
You've
would
got
have
more
more
friction.
barriers and more friction.
Exactly. So you have more friction, but what it means is that there's less gradient. So what causes turbulence is a difference between the friction at the boundary and the lack of friction in the centre. So the wider the gap between these two, the more of a gradient you get, and that's where you start getting slow air and fast air, which then starts rotating on itself and causing turbulence. So if you constrain it all into these smaller channels, you get less of a gradient, and it all moves in the same direction at the same speed. You get laminar flow. So yeah, by splitting it into these extra channels of this piece, we get massively reduced turbulence, measurably so, and very audibly reduced noise from the vent. So you can play it louder, lower, and cleaner. It's great.
Well, a lovely explanation of transmission.
There we go.
Okay, Toby, that was great.
Well, thanks very much
for that.
That's been great. Thanks.
We hope you liked that video. Our next in the series will be an interview with Nina, the lead product designer on the Lin Climax Solo 800 power amplifiers. Look forward to seeing you then.